Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's last lecture, and thanks so much for coming to the last lecture of this course. And firstly, some announcement. So I think I have announced the final consultation hours, but there is a slight change here for AMIA. So AMIA will have 2 hours consultation. So if you have any questions, you can chat with any tutor listed here, not only your tutor. And also another is about the announcement of the assignment 2. So I think Lucy has already announced some very important information about assignment 2. So firstly, you can check your grade online on Wattle. So if you have any question about your grade, so talk to your tutor, and your tutor will send an email to me, and in that case, I can revise your grade if there is any problem. And also, I think you can check, maybe 1 day before your final exam for your grade. So usually, I think I will upload all the updates, at that time. So if you find any problem for your final grade of your 2 assignments, so please check it 1 day before your final exam. And if there is any problem, you can send an email to me, for instance, right after the exam or something, so as soon as possible. So that's about the grade on Wattle. And also, I think some students have already collected their assignments during the tutorials in this week, but some students, I think, haven't. So in this case, for those students who haven't collected assignments during tutorials, you can collect from next Monday. So it's the announcement by Lucy from the administrative office. So that's about assignments. So any questions about assignments, about the previous lecture, about this course, or about final exam? Any questions? And also, I think on Tuesday, I uploaded the exam sample questions and also exam instructions. So my suggestion is just to read those instructions and also exam sample questions very carefully, because obviously that can help your final exam. And for instance, so in the question 1, so it's true or false question. However, I think basically it's the same in your final exam. You need to write the full word. That means all the letters of this true or false in your final exam to get your grade. Otherwise, you will not get your grade. So please be very careful when you read those instructions, because those instructions will appear in your final exam. So any questions about final exam? Okay, so I think for other courses, they will have a review lecture at the end. But for this course, because we basically review, I think, during our normal lectures. So when I usually mention about some new topic, so basically I try to review first. So in this case, in this course, we will not have review topic in this last lecture. We are still going to talk about PCA. But I think when I talk about it, I think you will have some review about the prediction, mean square prediction error, and also about multicollinearity, which are some topics in the multiple linear regression models. So in the previous lecture, so basically I talk about PCA. So what's principal components? So basically principal components are just the linear combinations of the variables, of the original variables. So what we want to do here is that we want to find some linear combinations of the original variables such that we meet all these requirements. So the requirement 1 here means that for two principal components, they are not correlated. So that means, for instance, if we have Z1 and Z2, which are both linear combinations of the original variables, and we need to determine those weights C such that Z1 and Z2 are not correlated. So the reason why we do that is to make sure that there is no overlap between Z1 and Z2. So that means Z1 represents some information and Z2 represents totally different information. So we need to make sure that the correlation of Z1 and Z2 equals to 0. So that's the first requirement. And the second requirement here is that we need to select those weights, those C, such that the variance of Z1 is maximized. And then we are going to continue to requirement 3. So that means we select the weights of Z2 such that the variance of Z2 is also maximized, but at the same time we need to consider this constraint, Z2 and Z1 are not correlated. And we can keep on doing that, and finally we can obtain the weights of Z1, which is C10 until C1k, and the last one is Zk, which consists of Ck0 to Ckk. So those weights determine, so basically using those weights, we can determine the principal components. So using those weights, we can determine the principal components Z1 to Zk. So usually if we have k variables, we will obtain k principal components. And in this case, those weights are called loading matrix. And by doing that, we can make sure the variance of Z1 is maximized. So that means Z1 contains the most information in the data, and then we will have the variance of Z2. So variance of Z2 is also maximized, but we require Z1 and Z2 are not correlated. So in this case, we can see instead of Z1, Z2 has another part of the most variation information in the data instead of Z1. So we can keep on doing that until we have Zk. So that's the idea for the PCA. So basically, by using one sentence, so basically we just want to find the linear combinations of the original variables such that the linear combinations can contain the most variation information of the data. And also we need to make sure different principal components are not correlated. So that's the PCA idea, to find those variable which has the most of the information, variation information of the data. So in order to see how to realize this idea in R, so we basically need to try this real data. So in order to help us understand it, we try two variables first, because it's easier for us to understand less variables, but it's just a toy example. So we consider x1 and x2, and x1 is the score of differential geometry, and x2 is the score of the complex analysis. So firstly we consider two variables, and then we will consider the full data set. So in this case, we have two variables, x1 and x2, and also k equals to 2. So that means if we use these two variables, we can actually construct two principal components because k equals to 2. So we can construct k equals to 2 PCs Z1, Z2. So we need to determine by using those requirements to obtain these two principal components. And in order to do that, firstly, let's just have a look at what the data look like. So in this case, if we have this scatter plot for x1 and x2, so basically we can find that this two variables basically are correlated, right? So that means our original variables x1 and x2 are correlated. So that's just some descriptive statistics to help us understand the data. And then we can use this principal component function to obtain our principal components. So in this case, firstly, we use this cbind function to obtain the data for all the variables. So this is the data for both two variables. And then we just put the data in this function. And if we use the summary function output, we can have a look. And in this case, we get some result. So I will explain the result. So firstly, we have the component 1. So basically, it's our principal component 1, Z1. And secondly, we have the component 2, which is our principal component 2. So if you still remember, we have two variables, and that will lead to two principal components. And for each principal component, we will have the standard deviation, so the standard deviation of Z1. And also, we have the proportion of variance and also cumulative proportion here. So what's the meaning of this proportion of variance? So this just means variance Z1 divided by the variance of x1 plus the variance of x2. And also, if we have a look at the proportion of variance here, so this equals to the variance of Z2 divided by the variance of x1 plus the variance of x2. So basically, it just means the percentage of the variation in Z1 or Z2 compared to the total variation. So in the denominator here, these are the total variation of the data. So basically, we just want to look at the percentage of variance of Z1 in the total variation of data, or Z2. So in this case, we can see here, 92% variation is included in Z1. So we can see here, by using the first principal components. So that means Z1 contains the most of the information of the data, 92%. And also this cumulative proportion here just means, for this variable, it just means the variance of Z1 divided by variance of x1 plus variance of x2. So the first element here of this row basically means the same, but the second one means the variance Z1 plus variance of Z2 divided by variance of x1 plus the variance of x2. So that means in the nominator, we actually accumulate the variance. So that's the reason why we call it cumulative proportion. So in this case, if we have two principal components, we will have 100% of the variation information. I think that's obvious because we just transform x1, x2 into z1 and z2. But we can see that the second principal component can only contain 7.9% variation information of the original data set. So that means Z1 contains the most of the information. So maybe I think we can only use that one to represent our whole data set because that one has the most of the variation information. So that's the idea of PCA. And also we have loadings. So the loadings are part of the loading matrix C. So I will explain why it's just a part of loading matrix C. And I will explain it later. But let's just look at the conclusion. So we have mentioned some conclusions here. So for instance, if we only have two variables x1 and x2, we will only have two principal components z1 and z2. And also, we mentioned about the percentage of the total variation. And also, z1 contains 92% of the total variation, and the second one only contains 8%. So that means maybe we can use z1 only to represent the whole data set. So that achieves the so-called dimension reduction. So we reduce the dimension 2 into 1. So that's the idea, to reduce the number of the variables. So far, any questions? And now let's just look at the loading. So here we have x1 as the score of the differential geometry and x2 as the score of the complex analysis. And if you still remember our formula, we actually obtain the principal components z1 from a linear combination of x1 and x2. And z2 is another linear combination of x1 and x2. And those C are called weights, or you can call those loadings of the principal components. So by using R, we can actually obtain the part of the loadings C11, C12, C21, and C22, and we can put it here. And we can use this C2 matrix to represent all the loadings and how to obtain it. So basically, firstly, we need to obtain the PCA result. So this is the PCA result. The test score.PCA is actually the result of this principal component function. So firstly, we need to obtain the principal component function. So this is the output of principal component function. And secondly, we consider to use $ to call the loading matrix. So here we use $ loadings, and also we need to use some square bracket. You can have a try. If you do not use it, that will not return a matrix. So you need to use this one column K to obtain the loading matrix. And here K equals to 2, because we only have two principal components. And also we need to consider transpose to make sure that you have each row represent principal component, and each column represent each variable. Because here, if you look at this matrix, each row represents a principal component. So I think it's better for us to keep consistent. So it's easier for us to understand the loading. So this is the loading. So basically, we have the values C11, C12, C21, and C22 here. So that's how we obtain this loading by using R. And also, if you compare this one to the loadings, I think, in the summary output, so basically, it is the transpose of this loading. So if you still remember transpose, so this T just means transpose of a matrix. So this is the transpose of the matrix in summary. So that's just a part of the loadings, just C11, C12, C21, and C22. And also we need to know what's the value of those constants. So what's the value of C10 and C20? So I just give you directly. So this C10 and C20 are actually determined by using the sample means of x1 and x2, and also those coefficients C11, C12, C21, and C22. So in this case, in order to compute C10 and C20, you need to compute the sample average, which is actually the center. So you can consider it as the center of x1 and x2. So in this case, by using this is the principal component analysis output and also dollar center, and in that, and we can call the values of those two sample means. And by using those sample means and also by using the results of this C11, C12, C21, and C22 results, we can compute C10 and C20. So how to compute it? So basically, you can just plug in the values of x. You can plug in the values of x and also the values of C11, C12, C21, and C22 earlier and obtain the result. But in order to make it a little bit easier, so we may need to use some matrix notation to help us. So these two, C10, C20, if we write it in a vector, it's equal to minus C11, C12, C21, and C22 times the x bar and x1 bar and x2 bar. And it is exactly equal to C tilde because we define C tilde equals to this loading matrix. C tilde times x1 bar and x2 bar. So by using some matrix multiplication, it can help us to compute this C10 and C20 more easily. So what we can do here is just to use this minus C tilde times x1 bar and x2 bar, and if we put it in R, so we just obtain tilde C, so basically our tilde C, and also this is actually the x1 bar and x2 bar, and in the middle we have the matrix multiplication. So this is the matrix product. So that means by using R, we can actually compute the value of C0. So I think this may be the only linear algebra we need to use, I think, in order to help us to simplify the computation. And in that case, we will obtain our value C10 and C20. And then if we just combine the C10, C20 with the other part of the loading matrix, so we can obtain all the loadings. So we can obtain C10, C11, C12, C20, C21, and C22 in this way. So basically, I just provide the R code for you. So if you are interested to obtain the complete loading matrix, you can compute in this way. And after you compute the loading, if you still remember, Z1 actually equals to C10 plus C11 x1 plus C12 x2, and Z2 equals to C20 plus C21 x1 plus C22 x2. So that's how we compute the principal components by considering the linear combinations and use the loading matrix. So in order to compute Z1 and Z2, you can actually write, for instance, you can write loop and plug in the value of x1 and x2 and also those loading matrix to compute those Z. But an easy way here is just to use some matrix multiplication again. So I will not explain it, but the idea, this formula, this matrix multiplication formula is exactly from the definition of the linear combination. So what you need to know here is that we can actually use this formula to compute the principal components based on loading C and x1 and x2. So in that case, we compute Z, and also Z, the first column here is actually our PC1, and this is our PC2. And if you have a look at the correlation of these two PCs, you will find that the correlation is 0. So that's basically our requirement, if you still remember. So that's the requirement, our requirement 1. So we find that the R output, obviously R output should satisfy all the requirements because the R function is designed to achieve those requirements. And if we have a look at the correlation of the original data, we find that actually the original data here is correlated. So that's the difference between PC. So for principal components, they are always not correlated. But usually for the original data set, we usually have the correlated variables. And the last one is just to show how to obtain this 92% of the variation in principal component 1. So basically, the variance of Z1 actually accounts for 92% of the total variation in the data. So that's just some explanation of the principal component output. And also, we have computed the correlation. So the correlation for the original variables, so which is correlation of x1 and x2 is 0.81. However, the principal components are not correlated. And also we can observe this result from the scatter plot. So this is our original data set. So the upper one is our original data set. We can see the correlation very obviously. But if you have a look at the lower plot here, so you can see basically we cannot find any pattern of PC1 and PC2. So in that case, these two principal components are not correlated. And the reason why we need two correlated principal components here is that we need to make sure that we do not have overlap for the information in PC1 and PC2. So basically, PC2 has totally different information compared to PC1. And so after the toy example, so now let's just look at some more complicated example. So in this more complicated example, we consider all the variables. So in that case, we consider our x equals to the whole data set, which consists of 5 variables, x1, x2, x3, x4, and x5. And what we can do next here is just to still use this principal component function. And in that case, we can transform these 5 variables into 5 principal components, Z1, Z2, Z3, Z4, and Z5. And by doing that, we can obtain the summary output of the principal component function, and which is here. So you can see we have the standard deviation, so basically the standard deviation of each principal component. And also we can know the proportion of variance explained by each principal component. So Z1 can explain 82% of the variation. So the first principal component can explain 82 of the variance. And if we look at the second one contains the I think almost 8%, and the summation of the first one and also the second one, if we consider the summation, so we will obtain the cumulative proportion. So that means the first one, and if we consider 2 principal components, so that will account for 90%. So that's the meaning for this cumulative. So basically, this cumulative just means that we accumulate principal component 1 and principal component 2. And similarly, for this cumulative proportion, it accumulates Z1, Z2, and Z3. So something similar here. And also we can have loading matrix. So this is the loading matrix, but actually we are going to use the transpose of this loading matrix. So I have mentioned it a little bit. And also you can see we have some blank here in this matrix. So those are just the means very small. I think should be very close to 0. So that's the first part, we get the summary output. So in that case, we can know how much of the variation can be explained by using the principal components. And because the first 2 principal components actually contain 90% of the variation, so maybe we just keep the first 2 principal components. Maybe the first 2 principal components are totally enough to represent the whole data set. And also, the reason why we need to use the principal component analysis is just to visualize the data. So we use the principal components to visualize the data. So why we need to use that? Because if we have 5 dimensions, it's really hard to plot these 5 variables in a plot, right? We usually have the scatter plot, so that means we only have 2 variables. So if we have 2 variables, it's much easier for us to visualize the data. And later I will give the visualization. So this is the, by using the first 2 principal components, we can visualize the data. So that means our data have 5 variables. So which is really hard to visualize by using the plotting tools. So if we can reduce these 5 variables into 2 principal components, so in this case, we can just use the scatter plot to visualize the data. So we can use this plot to view data. And so that means we have the values of these 2 principal components, and these 2 principal components account for 90% of variation. So basically most of the variation in the data. So in that case, by doing that, we can actually have a good view of data, and also we do not lose any variation information of the data. And each point here represents 1 observation. So if you still remember here, we have 25 students. So that means by using this plot, we actually show the 25 students, the scores of the 25 students, but we consider all the 5 scores of 25 students on this scatter plot. So that's the advantage. We can actually visualize the data by using the principal components. And the next is just to consider some details. So firstly, we need to get the loading. So what's the loading? Loading are in this matrix. And if we have the loading, we can compute the principal components. So that's the reason why we need the loading. And how to obtain the loading? So basically, I just copy the codes by using the toy example. So I will not explain the codes again. So these codes copied from the previous toy example. So that means we can have all the loadings. So that means for principal component 1, the C0 is 96, and also we have C11, which is the weight of the differential geometry, and also C12, which is the weight of complex analysis, and so on and so forth. So we can have a look at those weights. So the reason why we need those weights here is that we actually need to explain what's the meaning for principal component 1 and what's the meaning of principal component 2. We hope that principal component 1 and principal component 2, even if they are actually obtained by using a lot of requirements to maximize the variance, and also we need to make sure different components are not correlated. Even though these weights are from those requirements, but we will try to interpret those weights. So usually, it's the most difficult job when we use the principal component to find some reasonable interpretations. So for the first principal components, I think the interpretation, is okay, because if we have a look at all the weights, so basically all the weights are very similar. So that means we can interpret it as some average of the original 5 scores. So if we have the exact, for instance, if we have 1 divided by 5. So that's the exact, so that's the simple average, right? So in this case, even though we do not have this exact equal case, but we have very similar weights. So in that case, we can also consider it as some kind of average. So that's the interpretation of principal component 1. So something similar to this simple average. And for the principal component 2, so we can see the first 2 weights are positive and the last 3 weights are negative. So that means this principal component contrasts these 2 variables with the other 3 variables. So if you still remember, these two variables are scores of differential geometry and complex analysis. So these 2, if you still remember the context or remember the example, these 2 are closed book exam. However, the last 3 are open book exam. So basically, this second principal component measure the difference between the closed book and also the open book exam. So that's basically what we can do for this data. We try our best to interpret these principal components, but you can find that this interpretation is actually very vague. So that's the problem of PCA. The interpretation is really hard. So by using those loadings, so we can actually compute each principal component by using the formula Z1 equals to C1, 0, C11, X1, plus so on and so forth until C1K, Xk. And also we have Zk, and the formula is very similar. And in order to compute those, we need to plug in those loadings, and those loading values are in the previous page. And also we need to plug in the values of X1 to Xk. So in that case, I also just copy the codes directly from the toy example, and we can obtain the principal components. And say the result of the principal components is saved in this matrix Z. And we can find that the first column here is the principal component 1, and the second column is the principal component 2. So that's just how to use R to compute those principal components. And if we just plot this, we can actually visualize the data I have already mentioned. So sometimes the reason why we try to use the principal components to visualize the data is just to help us to clustering the observations. So here we have 25 students. So if we can visualize the data in this way, so we may have 3 clusters for these 25 students. For instance, we have this one in the middle one is the cluster 1 of those 25 students. And also we may have the second cluster and also the third cluster. So it's something related to the clustering analysis, but we do not talk about in this course. But you need to know that by using this kind of idea to visualize the data, considering the principal components, we can actually use this kind of visualization to help us to cluster the observations. So that means we have some similar feature so here we have cluster 1, and this is cluster 2, and this is cluster 3. So that means for the students in the cluster 2, they should have some similar features, otherwise they were not in the same cluster. So that's the clustering analysis. So very straightforward by using the visualization. And also we need to determine, so another question here is that how many principal components we should use. So usually we use this script plot. So in order to obtain this script plot, what you need to do here is just to use the script plot function and also PCA result, and then you can obtain this script plot. And what's this script plot? So basically the y-axis here represents the variance of each principal components. And x-axis just represents different principal components. And the standard to use this plot is just to consider the following 3 rules. The first is just to find most dramatic drop. So here, the most dramatic drop here is from the variance 1 to variance 2. So that's the first step. And the second step, after the drop, whether or not the variances are all small. So if we have a look at it, we can find that after this drop, all the variances are very small. So that's the second step. And if we have these two observations in the plot, we can find the point right before the drop. So the point right before the drop is actually 1, right? So if we try to use this plot to determine the number of the principal components we should use, so we need to consider conclusion here, use 1 principal components. But it's just some kind of experience summarized by statisticians. So if you really do not know how to determine the number of the principal components we should use, so usually you can use this script plot. But another choice here is that, for instance, in this case, the first 2 principal components can interpret 90%. So if you think 90% satisfies what you need, so you can consider to use 2 principal components. So it totally depends on your need. But this plot, this script plot, actually gives you some hint about how to determine the number of principal components. So basically, that's what principal component is and how can we use them and how can we interpret our output. So another very interesting topic here is that how about we try to use PCA in regression? Because in regression, we really have a lot of variables, x1 to xk, explanatory variables. And if we have this multicollinearity problem, so basically multicollinearity problem just means that x1, x2, and until xk, there is some correlation basically among those variables. So in this case, because the advantage of PCA is just to transform those data into not correlated variables. So Z1 to Zk are not correlated. So the idea here is just to try to use PCA to solve the multicollinearity problem. So will it work? So let's just briefly have a look. So we still consider to use the SAT data, if you still remember, in multiple linear regression model. So that means we use these variables to predict SAT. And also, in this data, we have we need to deal with the data first, and we remove some outlier, but I will not explain it in details. But finally, we can separate the data into training data and also testing data. And the testing data consists of the observations 14, 18, 27, and 42. So it's randomly selected by using this sample function. So if you are interested, you can have a look at it. So basically, we use this random method to select the training data and test the data. And then let's just look at the forecast by using different kind of models. So the first case is just to use all the variables. And you can find that we can actually see we have the multicollinearity problem because we have the VIF larger than 10. It's in your assignment 1. So in this case, we may try to solve this multicollinearity problem by using the PCA. So what we can do here is just to put those x variables in this PCA function. And I think there are 6 variables. So we will obtain 6 principal components in here. So, and also we can obtain the loadings by using the exact same code. And you can find that is it easy to interpret the principal components if you look at those. So you will find that it's actually very hard to interpret those principal components. So that means, if you still remember, for multiple linear regression model, I think the reason why it is widely used is that it has some kind of interpretation. For instance, beta 1 basically is the effect of x1, and x1 is some kind of variable. So here, x1 here is the takers. It has some practical interpretation. However, if we use the principal components, we actually have no idea about the meaning of PC1. So what is the meaning of PC1? It's not from our real life. It's actually the linear combination of those variables, but it's really hard to interpret. So that's the one disadvantage of the PCA. It's really hard to interpret. And so we can use those loading matrix and also the original training data set and obtain the principal components for the training data set. And how about and also we can determine the number of the principal components we should use by using the very similar script plot. So in this case, we can obtain, maybe we should use one principal component. So let's just try here, try to fit the data by using the first two principal components, even though in the previous plot we determined one principal component, but maybe 96% is better. So we try to use these two principal components to fit the data. So firstly, we put the two principal components in this data, and we just put it here in our regression model. So this is the regression result by using the PC1 and PC2, you can see. So that's the regression output. And you can find that because PC1 does not actually have some meaning in the real application, so it is really hard for us to interpret the meaning of the estimates. But the advantage here is that we no longer have the multicollinearity problem because x1 and x2 are not correlated. So we do not have the multicollinearity problem, so how about we try to use this PCA idea to help us to predict the data? So in order to use this idea to predict, what you need to do first is just to use the loading C and test data set of X to obtain the PCs of test data set. So that's actually a very important step. So that's the reason why I need to talk about the loading matrix, because if we do not have this step, we cannot use it for prediction. So if we use these first two principal components to predict, so we will obtain the result. Use the two PCs to predict. And we find the prediction error here is 215, but if we use all variables, but original variables, x1 to xk, we obtain 121. So that means the prediction result for two PCs is actually not that good. So how about we try to use all the principal components? Also, we do not have the multicollinearity problem. And this is by using 6 PCs, so basically all PCs. We can find that we can only get the exact same result compared to the by using 6 variables, same as. So that means by using the principal component analysis, we can never have better prediction result. So that's actually very important. So based on this investigation, we can find that PCA is actually very useful when we consider the dimension reduction to reduce the number of the variables. And also it's good for visualization. But when we use this PCA in regression, we need to be very careful because usually PCA does not provide a very good interpretation in regression. So that's the disadvantage of PCA. And another disadvantage here is that usually PCA cannot provide better prediction. So I think that's basically the end of this course. So I run PCA very fast because I need to announce very important information is that PCA is not included in your final exam. So just have some impression, just know something about PCA because it's actually good, I think, for real application, and it is really widely used. So what I want to say in the end here is that I'm really happy to teach this course, and I hope that you do learn something in this course, and really nice to meet you guys. And see you around in ANU and also RS Fest. And thank you so much. So any questions, especially for final exam?